Hi, I'm Bree, and being an engineer must be in my DNA. I always knew I wanted to get into an engineering or science field ever since I was a kid. My dad has worked for NASA for over 30 years, and I have two younger sisters who are engineers, but they're all electrical engineers, so they always give me a raised eyebrow for being the oddball chemical engineer. All of my best childhood memories were of building connects in our living room, piecing together mini robots, and looking at samples of dirt that I had collected from our backyard under my microscope, even if I had no idea what I was looking at. My job actually isn't that much different now, but I traded pajamas for a lab coat. I love making sense out of complicated problems and coming up with unique solutions. Now I get to do that every day at work, coming up with cool new ways to power aircraft and spacecraft. That's what the SPARRCI project is all about. NASA is helping enable urban air mobility and other electric aircraft concepts to the market that will likely be introduced by the 2025 timeframe, and we need next-generation batteries to make that happen. One of the most compelling reasons for next-generation batteries is the fact that state-of-the-art lithium-ion batteries can go into thermal runaway and release flammable vapors, which can cause fires with electric cars or electric aircraft. The degradation modes of these next-generation advanced batteries are not yet well understood and could result in additional safety concerns. In an attempt to contain and reduce the severity of battery fires, current approaches involve significant engineering of the battery enclosure itself, but don't actually reduce the likelihood of a fire. In addition, this approach adds substantial weight to the overall system, requiring even more energy due to the increased weight of the batteries. When significantly more energy is packed within the same weight or volume, it introduces an even greater risk of catastrophic or unpredictable failures in a battery. Existing measures to address fire propagation require heavy engineering implementations, and the specific energy or energy per unit weight plummets. While improving the specific energy of the battery is key to enabling electric aircraft, it brings about concerns regarding safety, particularly associated with fire. But it must be noted that typically the onset of fire is preceded by both chemical and structural changes in the battery, undetectable by existing external battery management technology. Early detection of such changes and analyzing the impact of those changes on safety in real time will enable fire prevention by taking failing cells or the battery offline. Our thin film sensors, capable of multi-parameter measurements and embedded within each cell itself, will provide early detection of chemical, thermal, and/or structural changes that are precursors to battery failure. Paired with a non-destructive evaluation technique, such as X-ray, CT, or ultrasound, to provide additional detection capability, the sensors can be employed to detect battery degradation. Feasibility of our SPARRCI concept will be shown by successfully accomplishing a few tasks. Manufacturing thin film sensors that are capable of measuring multiple parameters within the battery cells to detect failure mechanisms. Integration of those sensors into the cell while maintaining battery functionality, and a final demonstration of the concept at a small battery module level. This effort focuses on one key mode of degradation called lithium dendrites. The lithium dendrite can grow within a cell and cause an internal short circuit, which can ultimately lead to a catastrophic condition that we call thermal runaway and ultimately fire. With the deployment of sensors and non-destructive evaluation techniques, the data collected during battery operation will then be fed into multi-physics modeling efforts to develop failure models to provide real-time predictive capabilities for battery state of health. Given this approach, we believe that our effort will considerably enhance the safety of the aircraft while allowing advances in cell-level specific energy to be further realized at the battery level. Our approach also expands the operational window to allow for higher charge and discharge rates, while also reducing the weight of the battery pack and increasing specific energy by eliminating over-engineered packaging. We also believe that our technology will accelerate the adoption process for advanced batteries that don't have flight history but offer higher specific energy. This effort will accelerate the introduction of next-generation lithium-based batteries into urban air mobility and other next-generation electric vehicles, but also enable a near-term, safer battery with higher specific energy. These higher specific energy batteries will enable all-electric operation of urban air mobility vehicles and extend the range and increase the number of passengers for all classes of electric aircraft. This effort combines expertise in batteries and sensor research and development at Glenn Research Center, non-destructive evaluation techniques from Langley Research Center, and battery health management and prognostics from Ames Research Center. People are always looking for new, innovative, and better ways to travel, and we're on the cusp of a major shift in how we get around. It's exciting to imagine a world where we can hop into a flying car to get across the city, especially on our snowy, icy winter days here in Cleveland, where I live. A world where we can alleviate rush hour traffic because we have vehicles on the ground, but also in the air. Pretty cool, right? SPARRCI is doing our part to try to make electric aircraft a reality. We're trying to ensure that not only do flying cars have enough power to get off the ground, but also safely get you where you need to go.